Hello, welcome back. This is our last lesson in our electrochemistry module about electrolysis. So far, we have discussed at great length spontaneous reactions, and spontaneous reactions have positive voltage occurring in the forward direction. So they have a negative delta G and they have large equilibrium constant Ks. Those occur in what we refer to as voltaic or galvanic cells. And again, we mentioned that those are just two individuals' names, both Galvani and Volt. They're interchangeable terms for a spontaneous cell. But now we're going to turn our attention to a non-spontaneous reaction known as electrolysis. We must use chemical change from an outside source to drive the reaction. So we have to hook it up to a battery to force the reaction to occur. So our definition of electrolysis using chemical change from electrical current, the opposite of spontaneous occurs in the process of electrolysis. So the opposite process, the use of electrical energy to bring about chemical change. So for example, water can undergo electrolysis and decompose. When water decomposes, it decomposes into its elements H2 and O2. And it does so by an oxidation reduction reaction. So here we see a loss of electrons here from H2O going to O2, right? Because this is a -2 and this is a 0. And here we see a gain of electrons as our hydrogen goes from a +1 to a 0. So in this first one, we can see our two H2Os decomposing into oxygen, 4 hydrogen ions, and 4 electrons. Then we have 2 water molecules gaining 2 electrons, and it's decomposing into H2 and 2 hydroxides. And we can see this oxygen gas being produced here and the hydrogen gas being produced here. So when we look at this, we see the oxidation half reaction and the reduction half reaction producing the elemental forms of hydrogen and oxygen. Reduction half reaction produces the oxygen. The oxidation half reaction produces the hydrogen. This is a non-spontaneous process and must be driven with force with a battery, which is an external circuit. So we're going to start analyzing what happens in an electrolytic process. So again, this is a non-spontaneous process and it must be driven to force with a battery, which is an external circuit. So we're going to start kind of analyzing what happens in an electrolytic process to reverse the current to where now all of a sudden the oxidation still occurs at the anode, but it's positive. And the reduction still occurs at the cathode, but it's negative. We have some interesting things happening when we flip the direction of the current from the outside force. Here's an example where we have a non-spontaneous reaction brought about by using electrical energy to drive aqueous tin ions plus chloride ions, 2 units of chloride ions, forming the metal tin and the chlorine gas. Now notice that chlorine is leaving the terminal here, and you can start to see the metal of tin kind of plating out of solution here. Some other interesting things, we see that the cathode here is no longer positive. The cathode is a negative terminal, although it's still the site of reduction. The anode is now a positive terminal, although it still is the site for oxidation. The electrolysis of the tin 2 chloride, so that tin plus 2, chlorine gas forms at the positive anode. So we've got the positive anode, we've got chlorine gas forming. And tin metal is forming at the cathode over here. Applications of this process include something called electroplating. This tin would be considered plating out of solution, forming the solid form of tin from its aqueous ion. We pass it through a solution of salt and the metal simply plates out. And you can capture that if you wanted to plate over another metal. The material to be electrolyzed, either a molten salt. Molten just simply means a melted form of the salt. Salts are usually solid at room temperature, so we create the liquid form, or you can dissolve them into water and create an aqueous solution. So we have two different ways we can undergo electrolysis, and it's very important to note in the problem that you're studying. Are you using a molten form of the salt, or are you using an aqueous solution? And we'll decide why in the next slide, why aqueous solution is a little bit more complex. See the word molten salt, it means that the salt has been liquefied and can undergo electrolysis with a zap of electricity from an outside force, or like a battery. And if you hook up an electrical current through there and force the non-spontaneous reaction to occur at the cathode, which is negative now, we still have the site of reduction, the positive ion. And by the way, we're just taking an example of sodium chloride in molten form, which is now liquid. So in molten form, how does this undergo electrolysis? So how does this undergo electrolysis? Despite the non-spontaneous decomposition, note that the positive ion Na plus is going to gain 2 electrons to form its elemental form of Na, and it's in liquid form. At the anode, which is now positive, oxidation still occurs, but the positive terminal now forcing the current in the opposite direction, a non-spontaneous process. We know that negative ions of chloride, in order to form the elemental form of chlorine, we had to balance the equation, and we see the loss of 2 electrons. So that's why what we see when we balance electrons, loss of electrons equals gain of electrons, and the net equation to positive sodium ions forming its elemental form, and 2 chloride ions forming its molecular form of Cl2, diatomic form. And when looking at this net ionic equation, we just went from a positive to a 0. So our Na we can see as a reduction as it gained electrons, and our chloride is going from a -1 to a 0 is an oxidation. And we can see that it lost those electrons. And the electrons are moving through the external circuit under a force, and that force comes from an applied potential, typically an outside battery hooked up to this type of electrolytic cell. And the movement of positive and negative ions in the molten salt constitutes the current within the cell. This reaction is not spontaneous. The energy required for this reaction has been provided by the electric current. So because this is a non-spontaneous reaction, it is a negative voltage. That energy has to be supplied from an outside source in order to drive the reaction to completion. So it costs energy. Why would we want to do that if we needed to plate out for electroplating, or if we needed to produce a gas in its pure form? Forcing the decomposition of a salt into its elements can be forced through the process of electrolysis. Now, let's compare that to the electrolysis of an aqueous solution. So not just melting the salt, but going from solid to a liquid produces something called molten salts, just liquefying it. Now, what we're saying is we're taking the salt and we're actually dissolving it into water to create aqueous solutions. So electrolysis of a substance in an aqueous solution is a little bit more complicated than the molten salt. And that's because we have a competition between water, who we know can also undergo electrolysis, and the actual salt that was also undergoing electrolysis. So it's this little competition to see who is more electroactive. What can be oxidized or reduced in chemical processes? So let's model what's happening here. We have the electrolysis of sodium iodide. And let's just remember here that this is an aqueous solution. It's not molten. It's an aqueous solution. It's not melted NaI, it's actually dissolved in water. So we have the positive ion sodium. Remember, sodium with +1 would have to gain an electron to form its elemental form of sodium. We know that Na plus going to Na0 is a reduction half reaction. It's becoming more negative. So one choice occurring at the cathode, remember, the cathode is still reduction, would be the sodium. And if I check my standard table for potential values, negative 2.7. But we also know that water is competing at the same electrode. Now, notice if you look at your standard reduction potential tables and skim to the bottom of the back side of the paper, where it says Na plus E negative yields Na solid. And that's where you're going to see it's the negative 2.71 volts. I want you to skim up just a few until you find the closest water decomposition and find that reaction, that one closest by the sodium. It's the one farthest down the chart. It should be this guy. So this guy right here, where we have water gaining 2 electrons, forming the elemental form of hydrogen, leaving the solution basic. And you should see that it's negative 0.83 volts. Find that value, negative 0.83, for the forceful decomposition there of water forming hydrogen. And you compare that to the value of sodium. How do we know which one of those is actually occurring at the negative cathode? I can't stress enough, in electrolytic cells, the cathode is now negative, but it's still the site of reduction in a spontaneous reaction. I know the cathode is positive, but it's flipped in this non-spontaneous direction. The external force is moving the current in the opposite direction. So I want to compare these two values and see who's higher up on the reduction chart. What's going on? So if I compare negative 2.71 and negative 0.83, who's the more positive value? It's this guy. At the reduction site, at the cathode, this is the equation that will be occurring, number 2. Let's keep this thought process going for the other terminal, the anode. The anode is the site of oxidation. And remember, our example here was for sodium iodide. Na is plus, I is a negative. So now what's happening? We have 2 choices here for the oxidation anode. Find iodide. It's sort of high up in the list on the reduction table, maybe just above copper, where it says I2 plus 2 electrons yields 2 I negatives, and see that the table says 0.53. And just notice that I wrote it here the opposite way because we're looking at the oxidation of it. And remember, this table is for reduction potentials. So I just flipped it around. But the value is reported as a 0.53. I did not flip the sign, only the direction that I wrote it to show oxidation. But this is the same sign that's reported on the table. So what other reaction could be occurring at the anode? So this is number 1. Notice that there is this, that the equation, the generation of oxygen from the oxidation here of water. When water forms the elemental form of oxygen and H+, notice that to have a balanced half reaction for the decomposition of water at the anode, the oxidation loss of electrons, we see this value reported as 1.23 on our standard reduction table. On the table, it is worthy to note that this oxidation of water is written flip-flopped because remember the table is showing reduction. So if it was the other way, it'd be reduction. This is showing the oxidation. So we have a competition going on. who is the more negative number? Who's the least positive? That's another way we could look at it. So we can see that this oxidation happening here is the least. Here we go. The lower the number is where oxidation is going to be going on. So when looking at this reaction, to figure out what's happening at the reduction site, we have the sodium and we have our water. And we want to compare these two values. The one that is higher up will be where reduction is happening. The one that is least negative. So we can see that in this case, it's our water. For the oxidation, we want to look at who is lower, the lower number of the two. So in this case, we can see that it's the iodide. So when we're looking at these two half reactions, one of them comes from the electrolysis of water, while the other comes from the electrolysis of the aqueous from the NaI solution. And if we put these two together, we have our net ionic equation. We have our two waters plus the two iodides, creating H2 and two hydroxides, forming that basic solution, and the elemental form of iodine, I2. And then once we took and simplified, of course, remember we don't include our electrons in the net ionic equation, we were able to find the standard E cell, taking the cathode minus the anode, so negative 0.83 minus 0.53. And again, those values came from up here. We decided that our cathode was this negative 0.83 and our anode was our 0.53. And when we do this, we get an E cell value of negative 1.36 volts. And that makes sense that it's a negative value because the reaction is not spontaneous. The external battery must supply at least 1.36 volts to drive this reaction to happen. So I just want to go back real quick. If I were to go back and look at if I had a molten salt, the electrolysis is straightforward. The cathode is the site of reduction. Positive ions are reduced into their elements. The anode is the site of oxidation. The negative ions are oxidized as they form their elemental forms. The ion to the gas here for chlorine. There's no competition. It's just straightforward. Positive ion, negative ion, and redox. But if I'm reading about an aqueous solution, like here, then there is a competition between the sodium iodide, or whatever the salt is, and the water, because the water is also electrically active. It can undergo redox reactions. So when I compare the positive ion in the process of gaining here, so in the process of reduction, I use this value. I compare the positive ion to water forming hydrogen, so that negative 0.83 volts. And when I'm comparing the negative ion, I compare it to the water half reaction that generates oxygen, that 1.23 volts. This is always the equation you'll compare, the positive ion to this top one and the negative ion to this bottom number here. So these are the two that we'll compare to, the oxidation and reduction ones. And we want, for the reduction value, who is higher up? That's where the reduction is going to be going on. Let's see who is higher up. And for the oxidation, who is lower? Here's some more info about electrolysis. Electrolysis uses direct current, which is abbreviated DC. It has an external electrical force that's driving the non-spontaneous reaction. The cathode is the negative terminal, the source of electrons. So it is flipped. The anode is now the positive terminal. Electrons move towards it. And I just made some notes down here. What is true of all cells? Oxidation occurs at the anode and reduction occurs at the cathode. All cells. Now, what's true of voltaic cells? The anode is the source of electrons and the cathode draws the electrons. So our flow, the electron flow, is going from the anode to the cathode. That's our voltaic cells, our galvanic cells. In electrolytic cells, our anode has flopped and it's now the positive end, and our cathode is the negative end. So electrolytic cells, our electrons still flow from negative to positive. So it is flip-flopped. And again, this is needed, that external source is needed because this is a non-spontaneous reaction. It does not normally go from the cathode to the anode. That's why the external source is required. So voltaic cells goes from the anode to cathode. In electrolytic cells, cathode to anode. Voltaic cells or the galvanic cells are spontaneous. The electrolytic cells are non-spontaneous. Here we're going to highlight some of the components of an electrolytic cell. We said the anode is now positive and the cathode is now negative. That's the opposite of a voltaic cell. A spontaneous reaction is a voltaic cell. The non-spontaneous reaction is the process known as electrolysis in an electrolytic cell. Electrolysis of molten sodium chloride simply means that I have a melted form of the solid salt. There is an external battery forcing the current from the anode towards the cathode. Notice that it's a reverse polarity from the galvanic cell, also known as the voltaic cell, which are just spontaneous reactions. Let's look at this problem. Current is applied to a molten mixture of silver fluoride, zinc chloride, and aluminum bromide. What is produced at the cathode? What is produced at the anode? Well, first, let's recall that oxidation occurs at the anode. So, anode oxidation. Reduction occurs at the cathode, right? Both start with a consonant. Cathode reduction. It doesn't matter if it's voltaic cell or electrolytic cells. For both, reduction happens at the cathode, oxidation happens at the anode. However, the positive ions are being reduced. So the positive ion of, let's get this first one. The positive ion of silver +1, of zinc +2, and of aluminum +3. What's happening at the cathode is that a positive ion has to gain an electron to form its element. So positive silver +1 electron to make our AgS. And the same would be true for zinc +2. It would need to be added to 2 electrons to form its elemental form of zinc. And aluminum, 3 electrons to get to its elemental form. And then what's happening over here at the anode, for example, our fluoride ion to get to its elemental form of F2, so that would mean 2 of those, we would need 2 electrons that it would be losing. And the same would be true for the chloride and the bromide, going from its ion form to its elemental or molecular form, it's losing those electrons. Oxidation is losing electrons, so they would be on the right side. So the positives for the cathode, and the negatives, fluorides, chlorides, bromides at the anode. Do we need to consider water as a competitor? And the answer is no. There is no water at all because we just have molten mixtures. It's just these salts that have gone from solid to liquid. So when it comes to figuring out what is being produced at the cathode, who is being reduced? So we need to look and see who is the highest up on our potential table. So silver, if we find it, should be, all right, so on our standard reduction table, if I look for silver should be plus 0.8. Zinc plus 2 is on the back side of the paper, negative 0.76. And aluminum, even further down, negative 1.66. So which one of these is being reduced? I'm asking you, who has the most positive value? The most positive value will be the one reduced, and that is the silver ion. And then we're going to look at the same process over for the anode. And for the anode, for our oxidation, we want to look at who is the furthest down on our reduction table. Who is the least positive value? So let's see what we have for fluoride, chloride, and bromide. If you look at your standard reduction table with me, and fluoride should be a value of 2.87. Chloride, I believe I got 1.36. And bromide 1.07. So the negative ions are oxidized. The nonmetal most likely to be oxidized. The one that is the least positive, which would be the bromine. So we've got bromine, which would be at our anode because it's the least positive number. And for our cathode would be our silver, because it is the least negative. This next question tells us that current is applied to an aqueous solution of calcium sulfide. So because it's telling me that it's aqueous, we now have water in consideration. So what is produced at the cathode? Remember, a cathode is our reduction, so we have two choices. We've got our calcium being reduced, Ca2 plus 2 electrons, giving us elemental calcium, or we have water. So again, we have water on both sides because it's a competition, and we need to look up. So we've got calcium and we have hydrogen as two products, and we look up those values on our reduction table. For the calcium, we've got negative 2.87, and for the water, we have negative 0.83. So which one is higher on the chart? Who has the more positive value? And that would be this guy. So what is produced at the cathode? Hydrogen gas is produced. Then let's look over here. What's produced at the anode? So we have two options for our anode. Remember, for our cathode, the reduction, calcium and water. For our anode, oxidation, we have our sulfur, our sulfide, and water. So we have our S2 minus producing electrons and elemental sulfur. We looked that value up for negative 0.48. We also have our water in competition producing oxygen. And again, this is our oxidation. So these two values coming from our table. Who is lower on the chart? Who has the more negative value, 1.23 or negative 0.48? And that would be our negative 0.48. And again, it wants produced. What's produced? Elemental sulfur. Moving on, when we are counting electrons, we introduce a new term, current, and current is measured in amps. The number of moles of electrons consumed or produced in an electron transfer reaction is obtained by measuring the current flowing in the external electric circuit in a given amount of time. This is measured in coulombs per second. It's the definition of an amp, coulombs per second, electrical charge in a given amount of time. We use stoichiometry to determine how many grams of a metal will deposit in a certain amount of time. When current is applied, we could also solve for time, knowing how long it will take to keep this electrolysis reaction going, to plate out a certain amount of metal. And our formula really depends on our stoichiometric ratios. And with those ratios, it's really important that we want to cancel units out. So we're going to be using dimensional analysis. So this is just kind of showing how everything can cancel out here. If we have time and we multiply it by amps, which is coulombs per second, our seconds will cancel out. Then we're left with coulombs. And then if we multiply that by the reciprocal of Faraday's constant, which is Faraday's constant is coulombs per mole. But if I flip that around, so right now I've just got coulombs. So then if I flip coulombs per mole, so I would have then moles per coulomb, those will cancel out, leaving me with just moles. Then I'll be multiplying it by moles of metal over moles of electrons. So we'll have moles cancel again. And then to go from moles to grams, we're just going to use the molar mass. So let's just do some practice problems here so you can see. But once you start looking at stoichiometric ratios, it will start to make sense. Okay, so we have a current of 2.4 amps that's passed through a solution containing copper 2+ ions for 30 minutes, with copper metal being deposited at the cathode. What mass of copper in grams is deposited? So how much copper is being plated out? That's what we want. We want our answer in grams. All right, so this last slide, remember we're starting with time, but we want our time in seconds. So let's start with 30 minutes. We know that in 1 minute is 60 seconds. All right, so that'll get rid of our minutes. Next, remember we said, I'm going to flip back here, we're going to take our time and we're going to multiply it by amps because amps is also coulombs per second. So let's come back here and we're going to multiply it by our 2.4 amps. And then I'm going to write in my orange, which is equivalent to coulombs per second. We'll do that so that we can see that our seconds and seconds will cancel out. All right, next, I got to get rid of coulombs. Remember we said we're going to do 1 over Faraday's law. So 1 over 96,425 coulombs. And we said it's coulombs per moles of electron. Okay, that cancels these coulombs out. And let's go back here. Moles of metal over moles of electrons. Oops. And we know that for our copper 2+, that means I need 2 electrons to get to solid copper, right? 2 negatives plus 2 positives. So we have 2 moles of electrons for every 1 mole of Cu plus 2. All right, gets rid of those moles of electrons. Now I'm left with moles of copper plus 2. And let's look at our periodic table. I'm going to bring my math down here. And we know that there's 63.5 grams of copper for 1 mole of copper. So now we just need to do the math here. I need to do 30 times 60 times 2.4 times 1 times 1 times 63.5. Let's do that all real quick. So we'll do all of our top numbers, all of our bottom numbers, and then divide it out at the end. So check your math and check my math. That I did my total top divided by total bottom, and I got 1.422 grams of copper that was produced. Again, I started with time. Here's my time, and I times it by amps. And then 1 over Faraday's law, because I was left with coulombs, I needed to get rid of coulombs. Next, I took my moles of electrons and got my moles of electrons from up here. It takes 2 electrons to get rid of the copper 2 plus. And then I just went and looked at my molar mass of copper. That was able to tell me how many grams of copper was being deposited at the cathode. Let's look at another example. All right, we're given a current of 3.34 amps. It's passed through a nickel nitrate solution. And we can tell here that this nickel is a +2. So nickel ion solution for 1.80 hours. How much nickel is plated out of the solution? So we're doing the same setup that we did this last time. But here I'm given 1.80 hours. And we know that we need our time in seconds. So let's say that we have 1 hour is 60 minutes, and 1 minute is 60 seconds. Okay, so we're going to take our hours cancels, our minutes cancel. We're at seconds now, which is what we want. We got to do our times it by our amps. So we have 3.34 amps. Remember, amps is coulombs per second. Okay, that gets rid of my seconds. Next, I need to do 1 over Faraday's law. 1 mole of electron over 96,425 coulombs. So that cancels my coulombs. We need to look at how many electrons. If I've got nickel +2, that means that I need 2 electrons transferred in this reaction. So 2 moles of electrons for 1 mole of nickel +2. And then I'm going to look at the periodic table and do molar mass. 1 mole of nickel is 58.7 grams. And again, my electrons will cancel, my moles will cancel, and I'll be left with grams of nickel. So why don't you get on your calculator here and pause the video and see if you can get the same answer that I get. All right, hopefully you got 0.659 grams. That's what I got. Let's do one more where we work in reverse. So in this example, we're told that we have a current of 5 amps that's passed through a tin nitrate solution. Again, we can find out what this tin ion is. It'll be Sn +2. How long in hours would this current have to be applied to plate out 8.20 grams of tin? So we're starting on the opposite side. I'm going to write down our 8.20 grams of Sn. And anytime we have grams, hopefully it's been ingrained in your head. Grams, we want to get to moles. So I'm going to look at the molar mass of tin, 118.7 grams of tin for 1 mole of tin. And for 1 mole of tin, again, we're working backwards here. We want to look at how many electrons does it take, right? If we've got Sn +2, it takes 2 electrons. 2 electrons for every 1 mole of tin. Okay, what's next? Now I got to get rid of electrons. So we're going to use the opposite of, or Faraday's law, right? So for 1 mole of electron, we're going to have 96,425 coulombs. Okay, that gets rid of my moles of electrons. Now we need to multiply it by my amps. I got to have my 5 amps which is coulombs per second. So coulombs and coulombs will cancel. And then we got to get, we want to get hours. So we're going to go seconds to, we can go seconds to minutes and minutes to hours if you want, or we can just go right to seconds to hours, because we know that 60 times 60 is 3,600 seconds in 1 hour. That'll save me from doing another line. Seconds will cancel. So let's do our stoichiometry math here, or our dimensional analysis, I should say. And we should get almost 3/4 of an hour, 0.74 hours. And again, I just started with my grams. I went grams to moles, moles to moles of electrons, seeing how many electrons were used in this equation here to balance. And then using our Faraday's law, so I had electrons down here for coulombs, and then our amps, and then seconds to hours. Here is our Michael Faraday's as we wrap up our lesson on electrolytic cells. Faraday's constant we got from him. He was a very famous chemist, giving us words that we're very familiar with now in electrochemistry, like anode and cathode and anion and cation and electrode, all these concepts based on charge. And also, he was a very good organic chemist. So you'll probably learn more about him in upcoming lessons in chemistry. But I'm going to wrap up our lesson today on electrochemistry. We've gone through several examples of each type of equation and each type of topic.